Oh, the lights. Yes, yeah, would you get the lights for me?
I can't.
You can?
I have the C2.
Now,
That's awesome. It's all good.
Sorry.
It's all good. So we are starting chapter 10 today, which is about electricity. And I could say that I was really clever and had the lights left on when I started recording because I was talking about electricity. Turn it off, but I wasn't that smart. Electricity is the next subject, and we begin our conversation with static charges before we move into current flow. So today we're going to be talking about static electricity, and here we go. Take a moment and write that down. Okay, so electrostatic forces. We're talking about push and pull, and things like magnets and things like, electrical charges. And the forces that are generated by electricity are stronger than gravity, and you can see that with any kind of magnetic levitation. Maglev trains, or the new awesome maglev hoverboards that are being made nowadays. Magnetism and electrostatic forces, it's all the same kind of idea. Those are stronger than gravity. So you are stuck to the earth because of the force of gravity, but if there were an electrostatic force that wanted to levitate you, it could. And we're going to see some cool pictures of electrical levitation and magnetic levitation as we move to the next couple of chapters. They are based on charges. You can have a positive and a negative electronic charge, electrostatic charge. Charges have to do with the abundance of electrons somewhere. If something has more electrons than it should, then it'll have a negative charge. If it has less electrons than it should, then it'll have a positive charge. Like charges repel, opposite charges attract. So positive and negative attract each other. That's the basis of chemistry, right? And positive, negative repel each other. And so these are the general concepts of forces that we're going to be dealing with. Here's just another little picture to help you see that. Positive and negative attract. Positive, or negative, repel each other. You've probably played with static electricity as a kid. It's a thing that is kind of fun and gee whiz to play with. One of the things you can do is charge a plastic comb, and you can do that just by brushing your hair with a comb, and your hair will add a charge to the comb, and then you can take the comb over to little bits of paper or little bits of foil, or even just dust, and it'll get stuck to the comb. And so you've I'm sure played with these concepts here as a kid. It's fun to play with. We need to be able to analyze it a little bit more technically, though, now that you're in science class. So take a moment and write that down. I'll be right back. Electrical charge is a product of the forces within an atom. An atom has protons in the nucleus that are positively charged, and electrons in the electron cloud outside that are negatively charged. You can remove electrons fairly easily. You can't remove protons. Remove protons, you have things like nuclear explosions. So those are not something we're going to do in the class. But removing electrons is pretty easy to do. Here I have a latex balloon, and the latex balloon has electrons and protons that are balanced. Right now there's as many electrons as there are protons within a certain amount of error on this balloon. So the balloon is not charged. It doesn't have an electric charge. But if I were to rub it against something vigorously, I might rub off some electrons, and then I would have a charged balloon. So I'm going to do that. Okay, now my hair is not very long. My hair is not very long, so you won't be able to see too much. I can totally feel the electric energy moving around my head as I do this. You can't see my hair dance, but we could go up to Sienna, and we could see her hair move because she has longer hair, and you can see it attracting her hair. So what happened is I rubbed some electrons off of the balloon and onto my hair, and now the balloon has a charge. And then as I bring the balloon close to Sienna's head, the word is called induce. I induce a charge in Sienna's head. I didn't rub Sienna's head with the balloon, so the electron imbalance is only on the balloon. It's not on Sienna's head. But the imbalance here causes electrons on her head to move, and the hair then is
Should I
attracted
do it
to
on
the
that?
wood. So it's pretty cool. I should do it on you because you're probably just no seriously. You're probably just the right length of hair.
Make sure it doesn't pop.
Whoa.
Hold on. Those of you who might watch this in the future, here we have Andy's hair.
That's the wrong one.
There you go, Andy's hair.
That's Janine.
It's Janine's hair. You can't see it too well in the picture because it's too dark in here. That's okay. We have awesome hair attraction going on. Okay, it's not going to fall. So that imbalance of electrons creates a charge. Okay, and now the electrons are separated, and there's more electrons or less electrons than there should have been. And we measure that charge in a unit called a coulomb. And a coulomb is named after the last name of the dude who did this. But a coulomb is actually a lot of charge. One coulomb is a huge amount of electrical charge. The average electrical charges that you're going to work with in a lab or in your home usage of electricity are very, very, very small fractions of coulombs, microcoulombs, picocoulombs, things of that nature. But that's the unit of measure that we use. Okay, take a second. So when I was doing the balloon on heads, I didn't have to touch your head with the balloon for the hair to respond. The hair was able to feel the presence of the charge at a distance. And so unlike a push or pull where you have to be in contact with something, like pushing on an object, electrostatic forces are field forces. They act at a distance. It's kind of like the Force in Star Wars, right? You don't have to touch something. You can reach for the lightsaber that comes out of the ice at a distance. These are field forces. Electrostatic forces act at a distance. The further away you are from the source of charge, the weaker it is. You can't experience a field force at an infinite distance. But the closer you get, the more it comes into, the stronger it becomes. And we draw force fields. We draw force lines to help us visualize the direction and strength of the field. Force lines, field lines, are kind of fictitious. They were drawn before we realized that things like them actually do exist. You can make things like field lines in the real world, but most of the time when we draw them, it's just a model to help us understand something and picture something a little bit better. So this is an example of a field that's been drawn with lines, and we always draw the field lines going away from a source of positive charge. So if this had been a source of negative charge, all the arrows would have been pointing towards it. The arrows point away from a source of positive charge and toward a source of negative charge. And we would imagine that the field lines go in the directions that a small test charge that was positively charged would go if you dropped it into the field. So if there's a strong source of positive charge and you drop a little source of positive charge into that field, it's going to run away from the big source of positive charge. So these lines extend outwards in all directions from a source of positive charge. And then again, the lines all point inward to a source of negative charge. So the arrows always go towards that. And then when we bring positive and negative charges towards each other, these lines start to bend, and the lines go away from a source of positive charge and then bend back in towards a source of negative charge. And if it's straight across, then it's straight across. But if the lines start to come out the side, it's eventually going to go, oh, look, there's a negative charge over there. I want to be a part of that. And it points towards the negative charge. So these lines bend. They'll leave in all directions from the positive charge, and they'll wind up touching from all directions a source of negative charge. And then when like charges repel, they bend away from each other like that. It's leaving the source of positive charge and says, ooh, but I don't want to go over there either, and it leaves this way. So these field lines bend depending on sources of charge. Magnetism is very, very similar. This lecture is not about magnetism, but magnetism is another side of this kind of force. Magnetism lines leave from a north pole and go around towards the south pole. And so you have lines leaving from one object and touching the same object on the other side. For electrical charges, you don't see that happening. It doesn't leave from a positive charge and then come back around and touch the same object. It leaves a positive charge, goes to some other source of negative charge. Magnetism, it leaves and comes to the same object. So a little bit of a difference. Okay? Take a second and write that. Actually, no. I'll just keep talking. These force lines can be seen when lightweight atoms are subjected to the field. So they are fictitious things that you draw to help you imagine that. But then you can, in certain circumstances, actually take oil and sprinkle like pepper on it or some kind of powder on it and then subject that oil to an electric field. And all the powder and things will polarize and line up on the field lines, and you can actually see field lines for real. So I'll show you some pictures of that. These lines were being drawn and studied and used as a model before we discovered that they do actually exist in some way. Okay, so here's a video that I stop. When I charged the balloon and brought it next to Janine's head, or next to Sienna's head, or next to Angela's head, their hair was neutral initially. And then the hair jumped up towards the balloon. The hair was neutral. The balloon was charged. And so the question is, why did that happen? Well, there's this phenomenon called induction, where I'm going to bring an electric field over towards a neutral object. And that neutral object does not yet have a charge, but it responds to the presence of a charge by becoming charged itself. So what happened is the balloon has tons of extra electrons because they got rubbed off of my hair and onto the balloon. So I'm bringing a source of extra electrons over towards one of those ladies' heads. And there's lots of electrons up there. And so then electrons in their hair were like, ooh, negative energy up there, I'm going to run away. And the electrons actually moved from one side of her hair to another side of her hair and ran away from the source of negative charge. And that left the protons. And the protons are positively charged. And so the protons now are attracted to that cloud of electrons up on the balloon, and that's why their hair left their head and went up towards the balloon. And so the hair was neutral, but I created a charge where there hadn't been a charge before, and that is called induction. A strong electric field can create a complementary electric charge in a neutral object. A couple of pictures to help you with that. Actually, that's right, another video.